Hi, class, and welcome to Group 1's project entitled Data Analytics Keyword Groups, the implementation of a data analytics tool in the political field using Common Crawl files. Our group consists of Hector Anapan, Michael Machovis, and Rujun Shen.
Nowadays, the presidential election has become the hottest topic. All medias, news, and webs contain a huge amount of information about the candidates from two political parties. Bringing all the data on the cloud about this topic can prove to be very beneficial to analyze important points of this year's election in the United States. Our motivation is to create an application to analyze how much Democratic candidate Hillary Clinton appears on the internet news around the world during the specific month, which will be June, and figure out how many positive comments or negative comments are arising off the topic. We designed to run our whole application process on Amazon Web Service. We first search several common keywords which appear mostly on the internet and group them as keyword sets. Second, we create a MapReduce class which called wordcount.java and upload it to the Amazon Web Service. And then we use the Common Crawl dataset which is available on Amazon S3 to launch the Hadoop jobs. We will introduce you to Common Crawl later. After we get the output, which will be the keywords count results, we can analyze the results to figure out how many positive comments or negative comments which may influence the presidential election for the candidate Hillary Clinton. We implement Hadoop MapReduce for our project. Parallel processing will be a huge benefit to our project because there are tremendous amounts of data on the internet about the presidential elections, and by utilizing parallel processing, it will be greatly beneficial in terms of speed and efficiency during the compile and analyze process. There are two primary components at the core of Hadoop, which are Hadoop Distributed File System and the MapReduce Parallel Processing Framework. HDFS stores large files across multiple machines. It achieves reliability by replicating the data across multiple hosts. The advantage of using HDFS is data awareness between the job tracker and task tracker. The job tracker schedules map or reduce jobs to task trackers with an awareness of the data location. MapReduce engine consists of one job tracker to which application submits MapReduce jobs. The job tracker pushes work out to available task tracker nodes in the cluster, striving to keep the work as close to the data as possible. With the rack-aware file system, the job tracker knows which node contains the data and which other machines are nearby. If the work cannot be hosted on the actual node where the data resides, priority is given to nodes in the same rack. This reduces network traffic on the main backbone network. Common Crawl. Common Crawl is a non-profit organization dedicated to providing an open repository of web crawl data that can be accessed and analyzed by everyone. The Common Crawl data set contains approximately 6 billion web documents stored on a publicly accessible, scalable computer cluster. The entire Common Crawl dataset is stored on Amazon S3 as a public data set. The most current crawl data sets include 3 different types of files, which are raw content, text only, and metadata.
So now that we have gone over some of the design details of the program or of the application, um, we are going to talk a little bit about the implementation of the code itself and how the program runs and determines the output. So as two arguments, the program accepts an input location and an output location. So the input location is basically the folder directory that houses the files that are going to be sent to the mapper class. In this case, these are WARC files, which are web archive, which we'll talk about on the next slide. So we had to set the file format to the WARC file input format to be able to iterate and parse through each of the files to gather the information. And the output directory that is created from the argument cannot exist. It's just a part of the program that the output destination that's passed to it cannot exist. It writes the folder and then writes the output from the program as plain text. So the WARC reader. So WARC is a web archive format, file format. It was adapted from the ARC file format, which was just archive. They moved to WARC as part of a standardization. And this is what AWS provides. So we basically had to build our program to be able to support these types of files. Now, each of the files themselves, since they are archives, they contain many web addresses and the content of those addresses, so the HTML text. There were 7 files, 7 web archive files that we had used from June. And collectively they contained, as you'll see in the evaluation part of these slides, they contained nearly 400,000 different web addresses and content information. So the WARC file input format that we had set the program to passes the text object and an archive reader object to the mapper class. So we had to iterate through this archive record object and basically set up the input stream from that WARC reader and be able to parse it using an HTTP parser. So as the file was iterating through each of the web addresses, essentially we were gathering the URL name and then splitting each of the words and looping through the words to see if they had matched what you'll see in a couple of slides, any of the keywords that we had defined for this program. So we also had a sorting algorithm. So after the mapper class had run, it was using a context write function, which basically uses a key and value pair and passes to the reducer function. So in order to do this in one program, we used multiple mapper functions, and set the reducer to 1. So essentially our nodes could all utilize different mappers, but the collective outcomes would come together into one reducer so we could process everything that we needed to process. And one of the first things was to be able to sort, because each website or some websites would have multiple hits on words, which is what we were looking for. So we would need to be able to sort by website, so that later we could match to see if it passed our algorithm for a keyword check. So this would loop through each entry and create an array list of strings from them. This was then passed to the sort function, which basically compared the web addresses of A and B and would sort alphabetically. It was in a very easy function to implement, as it's part of the array list object functionality, and it's the easiest way to do this type of sort. So after the sort function runs, we reiterated through the array list and remapped as we went, so that our map now contained everything in alphabetical order by web address. So then this map was then passed to the keyword check function. So the keyword check function creates a page object array. And inside the page object are certain attributes like the web address name, and then it had a page count group. So our keywords were split into three different groups. There was keyword group 1, which was basically only words that pertain to Hillary Clinton. So Hillary Clinton, Hillary Clinton, no space, Clinton, words that would identify her as the individual. Group 2 contained different words such as BlackBerry, classified, email address, different variations of the ways of spellings. And our keyword function, the main purpose of this was to check to make sure that each web address had at least one keyword from keyword group 1 and one keyword from keyword group 2 to have a better chance of identifying a true match, that this was the type of web page we were looking for and it had the content that we were looking for. Now, each of these did count for all three keyword groups, but the main purpose was just as a check to be able to identify which ones were valid web addresses. And after the keyword check ran, we would be placing these back into an array and only pass back the web addresses that passed the check. So usually the web addresses at this point would reduce by a great amount because the previous, from the mapper class, there were many hits. So I would say probably maybe a tenth now passed and were passed on.
So, as explained in the previous slide, the main logic in order to do data analysis on this project is to find one or more keywords from each of the keyword groups that are part of the set of words being looked for. So we have used 7 web files out of 20,200 web files only in the June 2016 Common Crawl repository. And also, just to explain what a web file is, it is a Common Crawl file segment in the form of plain text. And each of these files is actually more than 116 megabytes, give or take. So we just took 7 web files, and there is actually, out of these 7 web files, there's a total of 396,991 websites found. So out of those thousands of websites in the web files that we have been processing as data, only 32 truly relevant websites were found, which is equivalent to 0.01% of popularity among Common Crawl data processed out of all these 7 web files where the data was obtained from. So let's just keep in mind here that the Common Crawl data set contains web pages with no specific category or topic. So they are just web pages from all over the internet, regardless of any category here. So as we can see here, the keyword-based approach that we're using in this program, it does give a relevant set of websites and the keywords obtained from them. So from the figure on the right, we can see some websites that the program picked up, as well as the keywords that it has found on the website. So evaluation results. As we can see figure 1 on the right, we see keywords such as Clinton, of course, Congress, department. So therefore, there's no real negative words that were picked up from this website. So what does this mean? This means that there's a very high probability that this web page did not contain any negative comments about Hillary Clinton, which in turn can be safely inferred that the web page's purpose was really to inform about Hillary Clinton, but not really to talk about any negative information about her. So in figure 2, in this case, we can see that the website did pick up some keywords They usually have to do with releasing negative content on the website. Let's say such as the keywords charges and corruption. So therefore, we can clearly deduce that this web page's content is really talking about the scandals that presidential candidate Hillary Clinton is involved in. So it's more of a website that has negative comments rather than positive comments. So measurement points. In this part of the measurement evaluation, we're going to talk about the scalability factor and the speed of factor that comes into play when talking about scalable programs such as the Hadoop cluster that we're working with here. So in order to prove scalability, we'll start by stating that slave nodes here need to be decommissioned, that is the word, meaning that they are gracefully removed from the cluster in order to decrease the cluster size, gracefully, of course. So the data size level. In regards to this, we have categorized the data size that we're using to be level 1 is 1 WET file, all the way to level 4, which would be 7 WET files. So in the measurements that we're going to carry out, we're going to run different scenarios that change as the cluster size as well as the data size level changes, trying out different combinations that will be graphically shown on the next slide. As explained earlier, the cluster size is the number of nodes that the Hadoop cluster is made up of. The minimum size is 2 nodes, since the cluster needs to have at least 1 master node and at least 1 slave node in order to process the data. In our case, the maximum number of nodes that we're working with is 5 nodes, which are made up of 4 slave nodes and 1 master node. Just for specification purposes, the VM flavor that we're using for all of these 5 VMs is 2 vCPUs and 4 gigs of RAM allocated to each VM. And the flavor name is T2 Medium. And we're going to continue with difficult evaluations on the next slide. So analyzing scalability. As we can see here, we have 4 graphs that are trying to obtain the processing time, which would be the time it takes to run the actual program from end to end, mainly based on the size of the cluster at the moment and as well as the data size level that is being processed. Some observations that we can clearly see regardless of the data size level is that the processing time decreases, sometimes almost linearly, the more number of nodes that are part of the cluster. So the bigger the cluster size, the shorter the processing time will get. Also, we'll see that the processing time changes. They're not always linear, so we're trying to, really understand what's going on here as if it should be linear, right? So, and based on our observations, it's most likely because of factors such as, let's say, uncontrollable changes that come out of using VMs. So, as explained in the lectures in the class, VMs compete for resource processing allocation for these resources when they are on the same compute node in the AWS platform. So naturally, the VMs used in this experiment have a high probability of competing for resources with other VMs in the same compute node if they are hosted in the same compute node. Of course, due to the open source nature of Hadoop, there will not be a guaranteed and constant level of service. So external factors will always play a part when experimenting with open source software. So performance degradation. So in this scenario, really the main point we're trying to tackle and understand is the scenario in which Hadoop jobs are running and slave nodes fell out of nowhere for any reason specific, actually. So as we know, the best way to make the slave nodes fail is really to just shut them down or just terminate them. So the issue with this approach sometimes is that when the slave nodes are killed, the master node will wait a certain amount of time before trying to reconnect to the failed node. So after a certain amount of attempts, really, the master node will give up and will show the failed slave node as a dead node, as shown on the figure on the right, which are the blocks highlighted in red. So when the Hadoop job is running before the slave node that was killed, if it's not yet recognized as a dead node, that is the actual terminology, The terminal will throw errors related to the disconnection between the fail node and the master node that manages it, which will directly affect the performance, of course, and the processing time of the job running. So we will see a screenshot in the next slide of what I'm talking about here. So the figure on the right, it shows Java exception errors being thrown when a slave node is shut down. Of course, the master node will try to contact all the slave nodes as if it would typically. And when it reaches to connect the fail slave node, a Java exception with the connection refused error, as we see in the first highlighted line, will show up, which means that the master node has no way of reaching the node, meaning the port's not open on the slave node side that is trying to connect to through SSH, of course. And of course, it also does not recognize it as a dead node, which is why it's still trying to connect to it, right? So as soon as the master node recognizes that the slave node is a dead node, it will stop trying to connect to it. So really, the main observation in this scenario was that the device from this scenario, I'm sorry, for performance degradation is that processing times as the cluster size decreases only actually takes a little less longer to process than the scenario where the slave nodes are removed from the cluster gracefully. So the main observations here is that unless the size of data being processed needs to be very large, it really needs to be very large in order to truly affect the cluster processing time. Otherwise, the active nodes will just compensate for the load that the fail slave nodes were supposed to take on.
So in conclusion, these are some takeaways and some things we had learned while we were building this project and thinking about this project. First, the Hadoop framework, that the open source nature, it's evolving, and there's always room for improvement. So that's kind of on a continuing basis. But we found out there was a lack of community support on handling the actual crawl files, which was a little bit of a difficulty, or like an obstacle, at least, to kind of get over being unfamiliar with those types of files. The Hadoop MapReduce approach gave us a lot of room because we did need a very customizable algorithm. It wasn't a templated data analytics type deal. So we needed that flexibility, which isn't provided from Pig and Hive because they do lack, you don't need to know Java to use those two, but we did want to use Java because we wanted to create the functions necessary to gather the information that was required to meet our goals. Two other things that we noticed with the project, that there is a high potential, or the potential of financial gains. It's very attractive to use these types of frameworks and pairing them with certain algorithms to collect data. And also, it's hugely beneficial to use data analytics to process large sets of data via the cloud, because you're using multiple nodes, so you're taking a load off, and it processes rather quickly. So those are just a few things that we saw with as a conclusion to this project. Thank you.